We did an activity yesterday where we tried to drop an egg inside a straw/tape apparatus in an attempt to minimize the force on that egg when it hit the ground. Okay, what do we want to do? We wanted to increase the stopping time of the egg so that we could decrease the force. We just watched a video of Cirque du Soleil where guys were being propelled upwards by a teeter-totter, and then they were landing on a mat. The mat was designed to increase the stopping time to decrease the force. There was guys holding the mat up in the air and then dropping it as the guy that was flying through the air hit it. Again, it was designed to increase the stopping time, decrease the force. When we have what I call a predetermined impulse, and a predetermined impulse is an impulse that's going to be the same no matter what. The car is traveling down the highway, it's going to stop. The impulse of that car is going to be the same no matter how it stops. The baseball is moving through the air, it's going to stop. The impulse of that baseball is going to be the same, whether somebody catches it and cradles the ball with her glove, or as like what happened the other night in the Los Angeles Angels baseball game, pitcher gets hit by a line drive in the side of the head, breaks his skull, causes bleeding of the brain, needs brain surgery. The impulse of the ball is going to be the same no matter what. What's not going to be the same is the force. If the Angels baseball player the other night, the pitcher, gets his glove up in time and is able to cradle the ball a little bit, the impulse of that ball is not going to be any different than when it hit the side of his head. But the force will be less because the stopping time is greater. When you have a predetermined impulse, an impulse that's going to be the same no matter what, an impulse that's going to be the same because the object is stopping, what you want to do here is increase the stopping time. Increasing the time of contact decreases the force. Why? Because the impulse isn't changing. The impulse is predetermined. So a little example up here with some numbers. We went through this yesterday before we did our egg activity. If your impulse is 10 and your time of contact is 2, then your force would be 5. If your impulse stays the same, but your time of contact goes up to 5, then your force is going to go down to 2. So the idea here is that the impulse is staying the same. You want to increase the stopping time. You want to decrease the force. There are situations, I suppose, where you would want to do the opposite of that. You'd not want to maximize the stopping time to minimize the force. Rather, you'd want to minimize the time to maximize the force, but not in very many cases, right? It's almost always the other way around. The other situation is when we have what I call a non-predetermined impulse. And I'm pretty sure in the English language, you're not actually allowed to do this. Put 2 hyphens in the same word. But I'm pretty sure that I don't care that you're not allowed to do it. I'm going to do it anyways. It's not a predetermined impulse. This impulse is not predetermined at all. It can change depending upon what you do to the object. Okay, when I stop an object, I can't change its impulse. I can only change its force. When I start an object, a golf ball sitting on a tee, a baseball that was moving in one direction, I want to start it moving in the opposite direction. When I start an object, I can influence the amount of impulse that it experiences. Typically, what I want to do here is increase the force, and the effect that that has when I increase the force is not decreasing the time. It's not related to time, but rather it increases the impulse. Hit it harder, hit the golf ball harder, the golf ball gets more impulse and it goes faster and farther. The other thing I can do, though, is increase the time of contact. The effect that has is on impulse again, not on force. If I increase the time of contact, that doesn't decrease the force, that increases the impulse. So when you hit the golf ball hard, it gets more impulse, it goes faster, it goes farther. When you follow through when you're swinging the golf club and you apply the club, you hit the club, or hit the ball with the club for a longer period of time because you have good form and you're following through, that's going to increase the time. It's going to increase the impulse. It's going to make the ball go faster and make the ball go farther. Yep. Yes, it should, yeah. You're increasing, I was going to make that green actually too, it doesn't really matter. So go ahead. What about the force? Yeah, I guess it's a vector, yeah. So understand the difference here, guys. When you're starting an object, it's not predetermined at all. How hard you hit it and how long you hit it for affects the impulse. But when you're stopping an object, what you do to it doesn't matter. It's not going to affect the impulse at all. It's only going to affect the force, right? Show you a little video on that one too. All right, one more thing that I want to take a look at with impulse now, before we finish up the concept of impulse and move on to another concept tomorrow. I want to take a look at an impulse graph. And specifically, when I talk about an impulse graph, I'm talking about a force versus time graph. F versus T. F on the y-axis, T on the x-axis. Whenever you see a force versus time graph from here on out, from the rest of Physics 30, I want you to think 3 words. Area equals impulse. I don't even care if you've read the entire question. I don't even care if you have read the question, if you know what you're being asked, or what, for that matter, what you actually are being asked. Doesn't matter. I want you to think those 3 words first. Area equals impulse. Every single time, no matter what, think area equals impulse. Because most times, you see one of these graphs, you're going to have to find the impulse. There's the odd time when you're not, but in the end, you're still going to need to find the area equals the impulse in order to get what you're looking for. The area between the x-axis and the line on an F versus T graph represents impulse. So if I do a graph that looked like this area right here is the impulse. I don't need an equation to find that. I just need to find the area. I have to know that the equation for the area of a triangle and the area of a rectangle is. Now, if that graph has some area above and below the x-axis like this, then I have to make sure that I pay attention to some signs. The area above the x-axis right here is positive. The area below the x-axis, and pay close attention to this, that's the area in here between the line and the x-axis, not some area down here. Okay, right here is the area that we're looking for. Since that's below the x-axis, we're going to make that a negative area. When I've found both of those values of area, I add them up. If the total area is positive, it's a positive impulse. If the total area is negative, it's a negative impulse. If it's positive, it's momentum gained. If it's negative, it's momentum lost. Now, remember what I said. We always think area equals impulse, but we're not always asked to find area. Sometimes we're asked to find the change in velocity. If we are, I still want you to think area equals impulse, but then once you find the area or the impulse, I want you to set that equal to m times delta v. Just stop writing for 1 second here. Why am I not saying use F times T? Like, what's the problem with using that equation here? I'm going to tell you to never use F times T when you're dealing with an F versus T graph. Why not? Like, think about that for a second. The F times T. Look, it's a force versus time graph. It seems to make sense to use F times T, right? Not M times delta V. What's the problem with that, Ethan? Yeah, exactly. What force are you talking about? Is it this force or this one or this one? The force is changing, right? What value of force do you use? Don't even try. Okay, don't even try. Once you find the area, which is the impulse, if you're looking for delta V, set that area or impulse equal to m times delta V. So you can see how if you're looking for impulse, you got to find area. But even if you're looking for change in velocity, not impulse, you still got to find the area. and then set it equal to m times delta v. Here we got an example, and then I'm done. You're not, but I am. 9.4, page 262. It says a golfer hits a long drive sending a 45.9 gram golf ball due east. Figure 9.22 shows an approximation of the net force as a function of time for the collision between the golf ball and the golf club and the ball. Let's look at the graph here now. Oh, look, it's F versus T. What thought comes to mind? Okay. No, that's legitimate. Don't use F times T. You don't want to do that. But the first thing that I want to come to mind is area equals impulse. Area equals impulse. We're going to circle this as well because it's milliseconds. How many of you caught that? I caught that, but I'm not sure that I did the first time, to be honest. That's an easy one to miss. A really easy one to miss. What's the impulse provided to the ball? What's the change in, or the final velocity of the ball? It doesn't really matter what I'm asked because I know what I'm going to do. I want to find the area. Which is the impulse, which is, because it's a triangle here, equal to 1/2 base times height. The base goes from 0.1 to 1.1, so it's 1 times 10 to the minus 3 times a height of 5,000. It gives me an impulse of 2.5. There you go. If I just trusted myself and thought area equals impulse right from the start, I've got the answer to A without even realizing what the question was. If you want to read the question first, go ahead, but don't worry about it. Hey, don't worry about it. If you want to just go area equals impulse and calculate the area right away, I promise you, you're not going to waste your time. You're going to need that, no matter what the question is. Question B says, what's the velocity of the ball at the moment the golf club and ball separate? I'm going to trace through this. I want you to tell me, say stop when the ball and club separate, okay? Stop there. Who says that's when the ball and club separate? Okay. Where's everybody else? The ball and the club separate actually right here. Not right here. Think about that for a second here. You hit the ball compresses. As the ball compresses, the force gets bigger and bigger and bigger. And then as you're falling through, the ball starts going back to its normal size and shape. That's when the force starts getting smaller. But it's still in contact. If the ball and the club are not in contact with each other, the force can't be 1,000 newtons right there. You have to have them in contact in order to have a force on the ball. So look, we're going to say delta P is equal to M times delta V. Looking for delta V here. We're actually looking for VF, but VI is 0, so same thing. Delta P, we already found. It's 2.5. M is 45.9 times 10 to the minus 3. I think we need to do that. I think it was 55 or 56. Somebody figure that out. $54 actually would round it to, no, 54.5, I guess. Area equals impulse. And then sometimes you have to do something else, but you always have to do area equals impulse. All right, here's your homework for tonight. Practice problems on page 462, please.